On the occasion of National Science Day, we join here to celebrate one of the greatest Indian scientists in history, G N Ramachandran. We all know that Science Day commemorates the discovery of the Raman effect. Today, we choose to celebrate Raman's impact by looking at the career of one of his most brilliant students. I would like to welcome you all to the online premiere of the film The Trials and Triumphs of G N Ramachandran, organized by the Science Media Center or SMC of IISER Pune. Since 2012, the SMC IISER Pune has been involved in the rising field of science communication. We create contents used in academic programs such as massive online open courses or MOOCs, communicate the research happening in the institute, and also provide workshops and internship to train the future generation of science communicators with various partners including National Council for Science and Technology Communication and Vigyan Prasar. Yet another aspect of science communication that we have also ventured into is the production of science themed interviews and documentaries. This is one such documentary. This documentary is directed by Rahul Iyer, an IISER Pune BSMS alumnus, who has attended multiple workshops at SMC and is currently interning with us. He was supported by Professor Harinath Chakrapani, the executive producer of the film, Dr. Madhusudan, primary consultant, and Vivek Kanadi, the producer of the film. This film has won the Best of Festival award at the International Film Festival of India 2020. With this introduction, let us begin the screening. We hope you enjoy the movie.
The early 1950s was a defining period for Indian science. Scientists and administrators set about to lay the foundations of a blooming landscape of science with two goals: to fast-track the development of the state and to play an active role in the global endeavor of science. In 1952, C.V. Raman, one of the greatest Indian physicists, received a letter in this spirit from A.L. Mudliar, a renowned educationist who was the Vice-Chancellor of Madras University at the time. Mudliar intended to build a physics department in Madras University where world-class research would be conducted. Naturally, for such a Herculean task, Professor Raman was his first choice. Raman, who was busy with his own institute, wrote back suggesting a candidate as good as himself, yet much younger. A protege of Raman, he would build and head the department with expertise, drive and vision. His research would make the department a talking point throughout the global scientific community. He would lay the foundations of an entire field of research in India. And so in October 1952, Gopalasamudram Narayan Iyer Ramachandran arrived at Madras University as head of the department at only 30 years of age. His greatest contributions would be career-defining for any scientist. He discovered the molecular structure of collagen, outracing elite scientists who had previously sought to discover the structure of DNA. And his crown jewel, the Ramachandran Map, is a fundamental tool used by hundreds of thousands of biologists worldwide today.
You have to give G N Ramachandran great credit because Ramachandran actually created a first-rate environment.
He always felt, I think, that we should be as good as anybody else in the world.
You could be competing with the top-end international groups, but you should have the courage to do that.
Ramachandran and team did not complain that they don't have computers to do it, they don't have facilities. They just wanted to do it.
Somewhere around there is when he started developing some psychological problems. With all that he was managing, none of it stopped his work.
In Madras University in 1952, I chose X-ray diffraction and X-ray crystallography in particular as the main theme for the laboratory, and the applications to biomolecule is the main aspect of this field that is to be pursued rigorously. However, I did not know where to begin. and on which molecules and biopolymers are the most profitable ones to study. The problem was resolved by the happy coincidence of visiting Professor J.D. Bernard to Madras during this time.
John Bernal was a British crystallographer and an important figure in the early development of structural biology. The problem of the structure of collagen was a hot one, and there was a race between top labs in Cambridge, Caltech, and others to solve it.
When I put this question to him, he told me that he was not very happy with the various structures of collagen that had been proposed in the literature at the time, and that the problem was wide open.
But why were researchers who solved the structure of DNA after this protein? For one, the problem was considered to be tougher than DNA. And secondly, even among proteins, collagen holds an important place.
Collagen is a building block of all the cellular material.
If you take the total body of a human being or any mammal and take the water out, the most abundant protein is collagen.
The bone, the cartilage, the tendons, they're all made out of collagen. It's a highly talented molecule. It can bend, it can twist because it can adjust itself to the surrounding pressures. People have now realized the utility of collagen for several practical applications.
The autoimmune diseases of collagen which are non-killer, like arthritis. Burn injury is very common in this country. Ulcers. There is a disease, Cephalosporin imperfecta, with just replacement of one glycine by an alanine. The longest life people live is 12 years. Can the society afford not to understand the genetic diseases of collagen, enforced by structural biology of collagen, and live with it?
You have to give G N Ramachandran great credit because, when he went back from Cambridge to Madras University, he, had to basically start up things from scratch.
He was a very hands-on person, and he built his own X-ray crystallography machine and things like that.
I don't think we can divide Professor Jina's work as, this is theoretical, this is experimental, this is computational. He was somewhere along rolled up into one.
The laboratory at the Department of Physics, University of Madras, was well equipped.
He was going to be the only person in that department. Everybody else was a student. And of course, built up the staff slowly.
It was done in splendid isolation. It could be seen as an advantage also. He was not biased by the thinking process coming from the West. He probably enjoyed, among the disadvantages, an advantage of being able to be very, very original in his work.
So for him, everything was a picture, everything was a 3D image in his head. That to me was his major strength. He could visualize and he could come up with answers long before he had the maths to codify it and put it down in a paper. And then, of course, he'd drive his students mad trying to get it just right.
So I met Ramachandran once. It was not a warm, fuzzy meeting, but it was certainly an intellectually interesting meeting. And after we finished talking, he gave me an assignment. Here's what I want you to do, he said. And because of my great respect for his work, I didn't react in the usual way I would have to some stranger telling me what I must go back and do. In fact, I went back and did it. So,
helping Ramachandran to solve the structure of collagen was a bright postdoctoral researcher named Gopinath Kartha. So to start out, Ramachandran had to find a sample of collagen. Fortunately, right next to his department was the newly opened Central Leather Research Institute. Ramachandran went over to talk to their deputy director, Dr. Nayudamma.
Professor Nayudamma, as a leather technologist though, he realized that what Professor Nayudamma wanted is a pure sample of collagen. Then he said, why don't I go and collect congruentile tendon? Nayudamma went to Australia for some meeting and collected a sample of a kangaroo tail tendon, put in his coat pocket and brought it to this country and had his colleagues purified for him.
Even if one does get pure collagen, you need to place a hair width sized piece in front of the X-ray. A camera might take a second to click, but X-rays could take multiple days back then. The X-ray pattern is like a negative, except it's just a few dots. An X-ray crystallographer tries to develop this into a picture using complex physics and mathematics into human-sized models. At a time when solving the structure of 100 atom molecules was a considerable job, solving the structure of a 10,000 atom protein was monumental. Ramachandran and Kartha spent months trying to get a decent X-ray pattern. Once that was ready, they began to construct a model. The lack of modeling kits did not stop them, as they used ribs of coconut leaves, cardboard cutouts, and wax to build and visualize their structure. But if the previously proposed models were interpreted with similar X-ray patterns, how could Ramachandran and Kartha develop a better model?
Kartha and Ramachandran proposed a triple helical model for collagen. That's the first time that anybody said that the collagen is a triple helical coil structure.
It was novel in several ways. One is a single strand of protein winding around a left-handed man, and 3 such coils winding around each other in an opposite-handed manner.
We used to make fun of the triple researcher of collagen. He got the inspiration from the rope the women used to get water from the well. Once I asked him very gently, where was the inspiration from? And he says, the manners in which the celestial bodies move around each other. He saw a helical model, and that's what he said was his inspiration.
The breakthrough to the collagen problem coming from Madras University took the structural biology community by surprise.
Pretty amazing, really. They got to the right answer before anybody in the US or Europe did, and they were supposed to be the main centers.
Ramachandran and Kartha's model of collagen soon gained fame as the Madras triple helix. For Ramachandran, the victory was more than about solving a difficult problem. His incentives were deeply linked to his 3 gurus.
So he said that he had joined the electrical engineering department in IISc to do PhD, and then somehow Raman and he got in touch. Once he and Raman had started interacting, this is what my father says, he went to the head of the department of electrical engineering and said, Ramachandran is wasted in your department, I'm going to take him off your hands.
He spotted his talent right away. C. Raman had special regard for G N Ramachandran also.
It was under Raman that I think Ramachandran's talents and interests in optics and crystallography really grew.
When he went to Cambridge, what he found was biology was in the air, because they could see that they had a set of tools in physics, and the tools could be applied to better understand biological systems. It was the biggest, the greatest group in the world at that time, so he also joined it.
During his second PhD in Cambridge, Ramachandran worked in Cavendish Lab, which was run by William Lawrence Bragg. He also got a chance to interact with a visiting professor from Caltech, Linus Pauling. Interacting with 2 of the greatest scientists of that time would deeply influence the young scholar. To understand their impact, we need to go further back to the beginning of structural biology. In 1912, William Lawrence Bragg, along with his father, William Henry Bragg, set the foundations of X-ray crystallography with their famous Bragg's law. They were awarded the Nobel Prize in Physics in 1915. Meanwhile, Linus Pauling was engrossed in understanding chemical bonds, the very forces that formed molecules. In 1931, he would propose the valence bond theory, which is a landmark in our understanding of chemical bonds. This period also saw the emerging importance of proteins and nucleic acids in biology. And so Pauling and Bragg joined the pioneering scientists who began to study biomolecular structures. They engaged in a friendly rivalry at the prospect of making history. The first race they embarked on was to describe the structure of the alpha helix, which shapes a vast number of proteins. Pauling and his team won this race in 1951. The next exciting race was for the structure of DNA. Members of Bragg's team at Cavendish Lab, James Watson and Francis Crick, would vindicate him in 1953. A couple of months later, J.D. Bernal informed him that the teams at Caltech and Cambridge, among others, were now chasing the structure of collagen. This was his opportunity to etch his name in history alongside leading scientists synonymous with early structural biology. Alongside his mentors who inspired him to pursue the study of biomolecular structures. But, alas, his victory was short-lived.
Subsequently, there was a paper in Nature by Crick and Rich, which said almost right at the beginning of the paper that the Ramachandran Karta model is wrong.
When the paper came out, he was very upset. And the accusation is that some of the stereochemistry of the model was not okay.
So all atoms are slightly sticky, they're attractive to one another. But if they get too close so that their electron clouds overlap, but they're not bonded to one another chemically, then they are very strongly repulsive.
Right from the time when the alpha helix and the beta structure for proteins were published by Linus Pauling, the assumption was they have to be the most stable possible structure.
Just based on optimizing hydrogen bonding, which was something that Ramachandran did, which was to recognize that you want to make the optimal number of hydrogen bonds, but at the same time, you can't bring atoms so close that they overlap with one another.
But they brought the three helices together a little closer than what probably was.
In a private letter to Ramachandran, Crick and Rich acknowledged that, quote, your type of structure was on the right lines and that the collagen problem has changed completely as a result of your work, unquote. The Ramachandran Karta model was the first instance that collagen was proposed to be a coiled coil structure. This was a key feature of the structure that the other groups had not deciphered. However, within months, other groups also published coiled coil models for collagen.
There is a controversy about that paper because apparently the Nature sat on it for a long time and they gave access to that work to Rich and Crick, who were also working on collagen structure.
Coincidentally, Gopinath Karta was in London at the time and his letters to Ramachandran shed some light on the matter. Ramachandran's paper was sent back for revision, and according to Karta, the general idea seems to be that the publication of our paper was purposefully delayed by months for them to work up an idea after seeing the manuscript.
All they did was just a little bit rearrangement of these helices to get rid of these short distances. So with that they could make it a little looser structure. And they actually published that paper almost simultaneously with the Madras group paper. That kind of became more of the accepted structure.
Sitting in India, you have no power in all this. So you just have to swallow your anger and put a brave face and smile. By today's standards, that would have been extremely unethical. But at that time, they did such things.
In those days, communication was absolutely almost zero. So it's not like, you're exchanging mails or picking up the phone and talking to people. Even your journals would take 3 months to come because they would come by sea mail and things like that. And it's again not a rigid structure. So what you see is sometimes what is the Ramachandran structure and you see sometimes what is the Rich and Crick structure. So it varies a little bit. I mean, the difference between the two structures is so little. But the basic idea about the triple helical coil structure was Professor Ramachandran's. There's no doubt about it.
During such tumultuous periods, Ramachandran had to rely on his constant pillar of support, his wife Rajalakshmi.
Somewhere around there is when he started developing some psychological problems. Manic depressive features were there, and that all fell on her shoulders. He was regularly going to a psychiatrist and maybe psychologist also, and getting treated. A huge number of drugs. When he took these drugs, he said, my mind is not sharp. At that point in time, I think my mother was of the opinion that all the sharpness is enough, you've done good work, now just become calm. With all that he was managing, none of it stopped his work.
According to science philosopher Thomas Kuhn, when there are inconsistencies in normal science, scientists have to conduct extraordinary research to lead a scientific revolution. This is the way science progresses. Coincidentally, around the time Kuhn published this, a real example was unfolding. As Ramachandran obsessed over his discredited Madras triple helix, he decided to do the unthinkable. He decided to challenge the knowledge of molecular physics. And what followed was nothing short of revolutionary.
It was just his boldness. All of us who worked with him, I think that was one thing we picked up from him, that you should be able to question everything which is there and to explore new ideas and new problems. And if you think something is right, just go and do it and stick to it.
GNR was bent on proving that he was right. And in asking the question, I think Ramachandran and his colleagues came upon what I would call a profound organizing principle of protein structure.
Ramachandran, being Ramachandran, tried to come up with a systematic way of finding out whether there was steric clash.
Now that raises the following 2 points. Number one, how do you judge whether a structure is good or bad? Number two, how do we generate good models as a starting point?
So the assumption at that time is that they can come closest, which is equal to the sum of their van der Waals radii.
This is inherently wrong because van der Waals radii are derived from gaseous state.
When I started looking up the literature, there are at least 15% of the data had distances less than the sum of the van der Waals radii between two non-bonded atoms.
So definitely the Crick and Rich's assumption that non-bonded atoms cannot come closer than the sum of the van der Waals radii is clearly wrong. And then how do you get the actual, the shortest approach distances between atoms?
They started an experiment to look at the basics of protein structure. The millions of proteins found in nature are all made from the same 20 building blocks called amino acids. Each protein has a unique combination of amino acids which determines the structure and properties of the protein.
I think the major principle to understand here, and if I may illustrate it with the pens which are there in my pocket, if I have two atoms, there's only one parameter which I can measure, which is the distance between them. If I now have three atoms, I can now measure two bond lengths and one bond angle. But now when I have four atoms which are connected to one another, now you can see I have introduced the element of three-dimensionality. So I am now rotating about a torsion angle. This is what in the polypeptides we call the Ramachandran angle phi or psi. So when you deal with torsion angles, you're actually dealing with a three-dimensional parameter. And this is what makes them so powerful.
Two attached planes can also be turned around to create a three-dimensional coordinate for the peptide unit. This immediately suggested to me that you require two torsion angles to describe the conformation of the peptide unit.
So, for example, I have here a CPK model. So you could see that each atom is represented by something that is a solid sphere. Here's a carbon atom. it's the alpha carbon. And as you rotate around that bond, there are 2 degrees of freedom for each residue, phi and psi. And you rotate here, and then you rotate the chain around the next local angle.
They considered for a minimal system of peptide. Like the Crick and Ridge, they also assumed the shortest approach between 2 non-bonded atoms is the sum of their van der Waals radii. You have the spatial arrangement of atoms. They checked all the non-bonded distances. If the sum of the van der Waals radii is shorter than the actual distance, then they considered the phi psi to be disallowed. Ramakrishnan, who was my thesis advisor, and he did his thesis with Ramachandran, and Ramachandran Map was his thesis work. He has to calculate the non-bonded distance between all pairs of non-bonded atoms and then check each one of them with the contact criteria. This he has to do for every single one of 360 into 360 combinations. And all that he had to do this work was a calculator of the present day PC size, which can do only 4 basic operations: addition, subtraction, multiplication and division. There is no memory location. You can't store the number. And it has no trigonometric functions. It's not a scientific calculator. So for trigonometric function, he has to use a book called as Clark's tables. So you can imagine him painstakingly punching the numbers in the calculator and then writing down the result in his notebook and then re-punching the numbers back into the calculator to do all these calculations. It is the fire in them that kept them going. And so Ramakrishnan told me that it took him from morning 9 to evening 6, 7, every single day, 1 full year. He didn't give up. Such a marathon exercise, numbers after numbers after numbers, to complete all these calculations. And interestingly, the result they have got is no phi psi value is allowed. That is an absurd result. Because proteins are existent, peptides are existent in living systems. They should have some phi psi value. If you do some work and then say that no phi psi value is allowed, then proteins and peptides cannot exist, and you and me cannot exist.
We decided to have a set of distances which are about 15% less than the sum of the radii.
They call it the contact criteria. So they call this as freely allowed or fully allowed contact distances, and then they call something as a partially allowed contact distances.
So Ramakrishnan did all the calculations again. Then the rest is history.
What's the great breakthrough in the Ramachandran plot? In biological science, there are not theories in the same sense that there are in physics. But then comes the Ramachandran plot.
There are a number of great features about it.
With the early structures, you're seeing all the atoms, and it's a forest, it's a jungle. That's the beauty of the Ramachandran plot.
It reduces the 3-dimensional complexity into a 2-dimensional representation, which is more easily perceivable by the human mind. Roughly about 30% of the phi psi combinations are only theoretically possible, and remaining 70% is not possible.
So it is, as far as I know, the only theory in all of biological science
where if an experimental result, which is a crystal structure of a protein, is not in agreement with Ramachandran Map, which is theoretical work,
then either you've got it wrong or you found something really new.
If your experiment is in violation of the theory, you suspect the experiment, not the theory.
It was done to validate the collagen structure. Now, if you calculate the phi psi values of the collagen model as proposed by Kartha and Ramachandran, they fall beautifully within the allowed region.
But in my view, the Ramachandran map was slightly ahead of its time.
There were problems in the early days of crystallography where some very incorrect structures had been produced.
Then the plot became a very important restraint.
So when you solve your structure, one of the first things you do is see what the Ramachandran plot looks like.
I think it took some time for the average protein crystallographer to be willing to be subjected to, to these rules and things.
Initially, it was thought as just a physics person's theoretical concept.
Like a very abstract piece of work, not particularly useful because you needed to have a huge computer before you could start using it.
But in mid-80s, I think the computer graphics began to be sufficiently advanced, sufficiently powerful, the resolution of the monitors, the speed of the graphics processing, a lot of manipulations and analysis and visualizations of protein structure implemented through computer graphics as opposed to in real life with physical models.
There was a very large expansion of protein structures.
That's when the Ramachandran plot really entered into the mainstream.
As the PDB developed in the 70s,
which has every single structure of protein anywhere around the world when they submit coordinates to that data bank.
They have requirements to check their maps before they were deposited in the PDB.
Probably if today we talk about bioinformatics as an area, perhaps he is the originator of bioinformatics in that sense through his so-called Ramachandran plot.
It's built into a lot of software and will continue to be built into software.
Today, several hundreds of thousands of protein structures have been determined, and every protein structure has to pass G N Ramachandran test.
The Ramachandran plot became central to my thinking and my life in structural biology.
And thus, the names of Ramachandran, Shashi Shekharan, and Ramakrishnan became known to every protein biologist across the world. Such was the caliber of G N Ramachandran. His own protein structure failed a test, so he created a test for every protein ever studied. It is remarkable that Ramachandran made foundational contributions from India in the 1950s and 60s. While researchers in established centers like Cambridge and Caltech would meet in seminars and conferences to discuss the progress in the field, Indian researchers trying to build the scientific landscape in India could only keep up through journals and by interacting with the occasional visiting professor. So it became important to identify research problems that would have a great impact. This could be seen in two contributions by Ramachandran. In the mid-1950s, he saw the potential of a phenomenon called anomalous scattering in X-ray crystallography.
Atoms scatter X-rays in a normal way, whereas when the wavelength of X-rays approaches a particular limit, an atom may scatter it somewhat anomalously.
This was first discovered by Byford, but Ramachandran was one of the first to use it to actually determine the structure of a compound. And so today anomalous scattering is very, very widely used. That's partly the result of work by Wayne Hendrickson and Keith Hodson and others.
In 1971, during a brief stint at the University of Chicago, G N Ramachandran got the opportunity to work on a technique called projection reconstruction, which is using 2D X-ray images to develop a 3D image. This area would later become very important as medical technology like MRI and CT scans developed. In both these cases, Ramachandran's contributions were perhaps not very significant in the final outcome. However, they display his knack of identifying the areas of research that would go on to become highly relevant. This talent, combined with his scientific genius and unparalleled drive to do research under any conditions, led him to build a research center of international reputation.
In post-independence India, he demonstrated that the highest level of science could be done, and it could be done in a place with rather limited facilities.
In fact, we had to go to Guindy Engineering College to use IBM 1620 computers. We used to get about 5 minutes, 6 minutes of time every day.
Ramachandran and team did not complain that they don't have computers to do it, they don't have facilities, they don't have money, and they don't have model kits to do all this. They just wanted to do it.
Ramachandran, by creating the Department of Biophysics and Crystallography, created his own environment.
Professor Ramachandran, of course, was a very towering researcher.
And he attracted the brilliant students to the department. It was only his personality that he could attract all the brilliant students.
It did an upwelling of the science in the campus.
I mean, he did all this work when he was in his 30s and 40s.
For a while, it was really on the map in the world. People, very famous people, Linus Pauling or Dorothy Hodgkin, they would come there for conferences.
Generally, it was conducted abroad. But he used to attract the scientists to Madras University, and we'll have a grand meeting of several Nobel laureates.
Imagine Nobel Prize winners being brought to Chennai city, all in one day in one platform, and the kind of influence it produced on the teenagers.
The research environment is quite important. It means that you have colleagues who are doing excellent work.
Professor Pauling came as a Sir C. V. Raman chair of the Madras University. This professorship was created by Professor Ramachandran in the University of Madras in honor of his guru.
Pauling, during the presidential address at the 1967 symposium, publicly congratulated Ramachandran for solving the structure of collagen. The recognition received by the department also helped them improve their infrastructure.
He had one of the first computers in India.
Professor Bragg wrote a recommendation letter to Government of India, right, suggesting that the Professor Ramachandran has been doing phenomenal work and he deserves a computer. But subsequently he got this computer as a gift from UNESCO. In fact, we were quite excited about having a computer and we could do lots of computation.
These earned him a number of accolades, including the Ewald Prize, the top prize in crystallography, and the Fellowship of the Royal Society.
I mean, for me, the great surprise was that he never got the Nobel Prize. And I think that what Ramachandran did for our subject was as innovative as many of the innovations that in fact resulted in Nobel Prizes.
And not getting the Nobel Prize is a lottery game. It's not something worth losing sleep on. But did it affect him? He never said so. It's there in the textbooks. So I think that's good enough.
The Ramachandran map was there since I can remember anything about proteins.
And there is no biochemistry textbook that doesn't have, very close to the beginning, a Ramachandran map.
Ramachandran's successes would not be possible without the complete administrative support under A.L. Mudaliar, and he certainly held up his end in making his department a center of world-class research.
And very often I've heard this term being used that Professor G N R was like a son to Dr. A.L. Mudaliar.
When Mudaliar's term ended in 1969, Ramachandran decided to return to his alma mater. Under the support of the director of the Indian Institute of Science, Satish Dhawan, Ramachandran founded the Molecular Biophysics Unit in 1971. He recreated an environment of excellence, as graduates of this department can be found in almost all structural biology departments in India.
The way his mind worked, I think he also wanted to always take up new things. So he got interested in what is called mathematical logic and things like that.
When we were students in IISER, Professor Ramachandran was there working on mathematical logic. He used to work in a room in the library and we used to watch him every day as a mystical figure. He used to come very early in the morning, go very late in the evening, just working alone like a saint. He doesn't interact with anybody in the system. I think he was deeply trying to develop the mathematical logic, and for us he was an inspiration from a distance.
And it also demonstrates the kind of commitment that he had to his science. He had that right to the end.
Even at that age, I think he was 75 maybe, he could think of new ideas, discuss it very well.
it would have been 91 or so, he came and visited me. He was busy going and meeting a professor in the US to convince him that a particular piece of work he had done was actually very significant for biophysics and all that. So, I mean, he was a driven person even then.
Indian science lost a great warrior in April 2001. But along with his remarkable contributions to science, Ramachandran also has one of the greatest stories in Indian science. The story of a man primed for scientific greatness, who would not only overcome many adversities, but turn some of them into his greatest achievements.
Those were exciting days, you know. When Ramachandran was a student there in the Indian Institute of Science, and we used to play in the college hostel there. You know. And I got into trouble at one time because the warden said, don't play here because you're probably breaking the tiles here, so you shouldn't play anymore. And he issued a warning. If you continue to play, I will have you dismissed from hotel. But we were young and we didn't care too much for this warden who gave that washing. And myself and Ramseshan were served notice by the hostel warden. And we had to appear before the director and all that. And Director Ganapati Iyer was a very wonderful man. He said, you young people, you don't live by a law and what not, he said something. And he simply say, you must at least say, I'm sorry for what you did. And then he winked at us and then he did like that. He wanted us to say, sorry because of the warden. He wanted to please the warden. But then he really didn't want us to express it. He was very happy that we did what we did. And then towards the end said, don't tell anybody I winked at you.
I hope that all of you enjoyed watching the movie. Let's now meet the people who played key roles in the making of this documentary. Rahul Iyer, Vivek Kannadi and Pushkar Soni.
Thank you, Hari. The starting point for the film was a conversation with Dr. Madhusudan in 2016 about his guru, Professor Sri Ramakrishnan, and his mentor, GNR. In 2019, at the beginning of Rahul's internship, I recalled this conversation about the genius of GNR. We got hooked to this project. Several student-driven films on scientists such as Fred Hoyle gave us confidence to go ahead. Harinath and Arnab took care of all the logistics for the project. Such projects are only possible when the mission of the institute embraces science communication. I am delighted to work with some of the greatest scientists and associates involved in this film. Here we are in 2021 presenting the film to a global audience. It is a moment to cherish. Thank you.
When I took on this project, I had two thoughts. One, why aren't more people talking about GNR? And two, it won't be easy to get interviews from so many busy scientists. But to my surprise, the code GNR was a password that opened so many doors for us. On my part, I was handed a fantastic story and put in touch with the best people to talk about it. I hope I did it justice.
It was about 6 months ago, in the middle of the COVID pandemic, that Rahul and Vivek asked me if I would do a voiceover for a documentary they were making on G N Ramachandran. I agreed, not knowing what it would entail. And several months later, we did a version which was critically reviewed by both me and our colleague John Matthew. We agreed it was not good enough and had a retake, which then went on as part of the film that won an award. However, perfectionists as we are at IISER, this was also not good enough for us, and it's only in the last week of February that we finally managed to come up with a version that is satisfactory for all of us.
Thank you, Rahul, Vivek and Pushkar for sharing the experiences you had while making this movie. Through the movie, we have got a glimpse of the kind of impact that GNR had on Indian science, whether it be through his research that made his team famous, or by almost single-handedly building the structural biology community in India. To better understand his influence, we shall now begin a panel discussion on this topic, the Ramachandran impact on Indian science. Our panel today involves scientists who have either directly or indirectly been under his umbrella of influence. The panel will be moderated by my colleague, Dr. M.S. Madhusudan from the Biology Department in IISER Pune. Madhu did his PhD at the MBU and his lab works on computational and structural biology. He has provided valuable insights and guidance throughout the project, for which we are all grateful. I shall now hand over the stage, so to speak.
I want to describe only one incident where it shows how generous and how intelligent Professor G N Ramachandran was. I was assigned a project on anomalous dispersion of X-rays and I was studying it. But I was always interested in a theory called dynamical theory of X-ray diffraction, developed originally by Ewald. But nobody had combined, on the one hand, the vibration of atoms in the crystal and the dynamical theory developed by Professor Ewald. So it occurred to me that I should try to combine the two and see what happens. One day when researching in the library, I got a clue, and based on that, I expanded on it and developed all the necessary mathematics in terms of Fourier transforms and I wrote a paper. Then when I gave it to him, he was very happy, he pleased, and then he wrote my name only on it and then told me to simply acknowledge him. I was very happy, and then he took and wrote to Professor Ewald and forwarded that paper. On receiving that, Professor Ewald was very interested and immediately accepted the paper. But a little later, he had some questions and he was wondering whether some people might know, and Professor GNR wrote a very strong letter defending my work and also asked me to do a little more expansion of it, which I did. And then he stood by very firmly with me and then sent the paper back to Ewald. Ewald accepted the paper finally. I was amazed that he was so generous. He simply asked me to publish it on my own name, and then he wanted me to be simply acknowledged. That's what I did. I have great regard for him, All my 4 years of PhD work, we had interacted many times. Every time I came out of his room with a greater physical intuition. It's very, very remarkable that I had a very lucky to have such a very good professor, and I'm so thankful to him, and I very much respect his memory.
What is GNR's centenary year. He was born in 1922. I want to congratulate Rahul and Vivek on what I think is a very well-made film. The Vivek and I first spoke about this when he helped me put up material of C. Ramakrishna's lectures on YouTube. C. Ramakrishnan, as you've known from the film, is one of the co-creators of the Ramachandran Map. And I was telling him then that we should get C. Ramakrishnan, CR for short, his views on the Ramachandran Map. Sadly, we could not get CR's views on this. But what we have today is a whole host of other very accomplished scientists who are in some way connected to GNR. But before I can introduce them to you, this is live on YouTube. And for those of you who are watching and have questions for the panelists or even about the film, do write it in the chat, and we'll see if we can take it sometime towards the end if time permits. Or even if we cannot, it will serve as important pointers on how we archive material that is GNR related. So introducing the panelists in no particular order of preference really. The Indian Institute of Science, and someone who was recruited by GNR to MBU in the early 70s. Professor Manju Bansal, a PhD student with GNR in the mid 70s, and later faculty at MBU and the founding director of IBAB. Professor Jayant Udgaonkar, the current director of IISER Pune, and perhaps the one person who will give an outside perspective on GNR and his legacy. Professor Vasanta Patabi, a former head of the Department of Biophysics and Crystallography in Madras University, and who was a student at that very same department that was founded and headed by GNR at the time. Likewise, Professor N. Yatindra, who was also a director of IBAB and a student of that same department in Madras University that GNR headed and was a student at the time GNR was the head. And finally, Professor Gayatri Panangat, a colleague of mine here at IISER Pune and someone who got her PhD at MBU. So to begin this conversation, I want to dwell into a little bit of the history and figments of which were mentioned in the film itself. And I want to try and do this in some order of chronology. So first, over to Professor Vasanta Patabi and then to Professor Yatindra, to give us some kind of an idea or an account of what it was like to be a student in the department that GNR headed, about the excitement and about the inspiration, all of which we got teasers of. So Professor Patabi first and then.
Hello everyone. Actually, I was fortunate to be there when he was there in the department. He's kind of the inspiration he gave to the students, the time he spent with them, the time he spent in science, talking about science. It was always science in the department. And I could see how thriving the department was. It was full of life. Once he left, the void could not be filled for 10 years. That kind of inspiration he used to give us. And he guided all the students. I mean, in the sense, there were teams formed on different subjects of biophysics, but he will take care of every one of the students, make sure they get their fellowship, they discuss, they understand science, he will teach. So that was really amazing environment. And I could see that, he will sit through all the seminars. All the seminars, help them, guide them where they are stuck, where they are wrong. So all those things made such a lot of difference for the students of that time. And the students he got also were very bright students, because I don't know whether he had a special ability to point out at the students. And they were hardworking, all the same time having fun in the department. It wasn't he will give some job today and say, oh, you take your own time. And then he'll say, finish it tomorrow. That kind of, he will push us, but we will not feel he is pushing us. And he will give any assignment to any student. It wasn't that only his own students got the assignments. And I would say we were all excited, happy at that time, and I can never forget those days.
Professor Yatindra?
Yeah, we all feel very proud and privileged to be part of this department. I'm referring to the time frame, sometime late 1966 and 70, and then my entry to the department was accidental. In fact, my morning sometimes in September of 66, I just barged into a room without knowing or it's temper and all those things. And I just create my mind. And he was quite surprised. He said that you will not be able to take it to the place which you will do. And of course, he has to command. Join the course, successful, then I will take it. I was lucky having there. There. The kind of he brought, the kind of organization he had, symposium. After I joined, there was minus bowling to say the board. I was observed. He stayed in the department. He was lecturing to us. Not just about that. It was the Jena used to lecture. He spoke about crystallography. I think the instructor was mind group and the community. But then the situation is still on. So, great time enjoying. But the third discovery we were started discussing about the series. Of course, I was a very junior there. The discussions with Helical and Body and other people were discussing. It was huge inspiration for us, and it was really fantastic to be part of it.
So thank you, Professor Yatindra. Some part of it was slightly inaudible, but we'll hopefully collect that glitch as we go on. Professor Manju Bansal, you were his student too, but in a slightly different setting from what Professor Vasanta Patabi and Professor Yatindra just described. These were the Madras days, but you were in the Indian Institute of Science. So what was it like there? And a different setting, different kind of atmosphere?
Yeah. Yeah, I heard you. Yeah.
Yeah. So, Professor Manju Bansal, how was it as a student in MBU and in IISc?
Everything seems to be echoing. Yeah. So I joined in 72, a year after actually GNR had set up the MBU department. So I was in the second batch of students joining. So as you pointed out, so there's a lot of delay in the sound. Yeah. So the thing is, the MBU was just starting, so it was hardly a department. I mean, I think the word unit, which we continue to use, was very true at that time. So, and when after I had joined, I didn't actually know who I was going to work with. And it was only 3 months later that I was informed that I would be working with Professor Ramachandran. So it was.
Please do continue. You're coming through fine.
Okay, yeah, all right. So after we, so the moment when I was told that I would be working with Professor Ramachandran, it was actually very interesting because a couple of the people who had come from Madras actually they tried to really scare me by saying that, you know, oh, you're going to work with Professor Ramachandran, you'll find it extremely difficult. I mean, today people may say, so people may say that, you know, he was very friendly and nice, but by the time he had come to Bangalore, he had already had an aura about him. And there was a lot of worries. And so I was very apprehensive about working with him. But once I met him, and, you know, which happened in October, about 3 months after I had joined as a student. But then he explained to me very briefly what kind of work I would have to do. And I think the way he was very clear about what exactly he wanted done right in the beginning. And the problem looked very interesting. It was a very complex problem because, as you would have all realized, collagen was an extremely, among all the protein secondary structures, the triple helix is the most complicated one. So I was very scared about it. But I think somehow he did give you that confidence that you could handle it. And I think that was very important. And the other thing about interacting with him was that he he wanted things to be done fast, as Vasanta also pointed out. And even though IISC had a computer, we had very little access, you know, the amount of time available for it was very, very less. So it was a day and night. I mean, it was like working 20 hours a day to kind of be able to deliver the results in the time frame in which GNR expected. But since I had come to MBU, in fact, mainly because I had heard that Professor Ramachandran, in fact, otherwise I was planning to go to Madras. But then I came to know that he had moved to Bangalore to IISC. So I moved here. And MBU at that time had only 3 or 4 faculty, and so we could interact with all of them. So MBU itself was a very friendly and nice department. So what I found was, even if I could not always talk to Professor Ramachandran, I could actually go and talk to Professor Ramakrishnan or Professor Shashi Shekharan. And so, you know, it was difficult, but not impossible. And I could be able to manage talking to him. And one thing I noticed was that if he didn't like the results, he would be unhappy about it, and we would all be scared of, you know, what he was going to say. But then I think once he thought about it, I think he accepted things for what they were and encouraged us to keep working. So I think that was the first thing that I learned maximum from him, that one is to take up challenging problems, not get scared and give up very fast, and then, you know, just keep working on it, and not just try to do things as like a, you know, doing a small delta research on some existing problem, but to take up, you know, explore new ideas and challenge. And I was much more grateful to him after I finished my work and I left, because I found that he could present my thesis work much better than I could. And many places which I visited subsequently, so many people told me that they had heard about my work from Professor Ramachandran's talks, and they thought I had done some great work. So that was extremely, and I think that was the kind of person he was. And I think one major thing, apart from trying to do good science, that he taught me was that, you know, to give, acknowledge the work done by your juniors, your students, and your collaborators. And I hope I was able to carry that on throughout my career too.
Thank you. We'll touch on that a little bit in a few minutes.
Yeah.
But I have an important question for Professor Balram. And this is something that the movie makes a fleeting reference to. There was a map of India, and there were locations of the various institutes, and where people from MBU who either graduated or had some connection with it are now members of the faculty or are leading the institutions there. Now, all of this seems to be built around uh, the the structure that G N Ramachandran created. Of course, there is also all the people who worked at MBU and trained all these people, but it seems to me that you can trace all this back to G N Ramachandran. When you have somebody of that intellect, it seems that you're not just building a research group, but you build up an institution which in itself helps sustain science. So what is your perspective on that? You, Professor Balram, you need to unmute yourself.
Sorry?
Yes.
I heard your question and I also read your email.
Okay.
Professor Ramachandran wasn't an institutional builder in the conventional sense. When we think of institution builders, we think of Homi Bhabha or we think of Shanti Swarup Bhatnagar and so forth. Ramachandran was a builder of science. And what he really did was his unrelenting emphasis on scientific research meant that everybody in a department in which he was now focused on science. And the result is that science just spread. And science spreads through people, not through institutions. And I think what you really now see are people who have graduated from the departments that he started, who are there in all those places across India. In fact, I'm seeing the map for the first time. And I think that is a greater tribute to G N Ramachandran than anything else.
Perhaps we should update that map and show and show a world map instead. I should tell Rahul about this. Professor Durgankar, you are someone who has had an association with MBU in the sense that you have collaborated with people there, even though you are not directly related per se as the other panelists are. So, as as that sort of an outsider, what is your perspective on the works of Professor Ramachandran and on the kind of science that was built around him and spread across the country and the globe? You need to unmute yourself.
So I learned about the Ramachandran plot from textbooks, and this was well when in my college days, and it was clear that it was a fundamental discovery, especially when I looked at a very early book on protein structure by Richardson and Guys. Subsequently, I was a student of chemistry, but when I went to Cornell to do my PhD in biochemistry, we of course studied the IISER map, and but the amusing thing was that I was doing my research, my project in a lab which was located in the physics department, which was adjacent to the chemistry, and one would go to the chemistry department for eating snacks or whatever. And invariably, occasionally, one would run into Harold Shiraga, who was a pillar of protein chemistry until his death last year. Shiraga was 99 years old when he died, so he was a contemporary of Ramachandran. And the one thing Shiraga would, the first time I met him there in the elevator, he asked me, "Are you from India?" The next question was, "Are you from Madras?" Not from Bangalore, but are you from Madras? I mean, his entire interest in India, I think, was based on the fact that Ramachandran was from Madras and he had done this phenomenal work in Madras. So it's something which I think this work which he did, I mean, it's very clear from the documentary that it's had an impact in protein chemistry in general, all across the world. Every protein chemist, every structural biologist has to use it in some way or the other. You cannot teach elementary biochemistry without teaching the Ramachandran plot. It's something, worthy of a Nobel Prize, and Ramachandran should have been given a Nobel Prize for that piece of work. There are no two ways about it. I have absolutely no idea why he did not get a Nobel Prize for that. And it's a shame that he was not given one. And if one looks at post-independent India and one thinks of scientists who have done absolutely world-class science, I mean, his name is right on the top. There's no two ways about it. And he, he has done something which I think no other scientist in the country has been able to do, make a fundamental discovery, which is in every textbook you can look at in the field of biology or in biochemistry. So when I was finally applying back to India, my first choice was to get a job in the molecular biophysics unit, and they said no to me. I was offered a job in other departments in the IISc, but that was my first priority, and probably I didn't join the IISc and joined the TIFR because I didn't get my first choice there. But, when I was thinking about coming back to India, the important point to me was, is it possible to do good work, great work in India? And the one example that I knew from textbooks or from reading is the work done by G N Ramachandran. And so it was, that one example was something which stood out and which, could kind of, it convinced me that, it's possible to do world-class science in India. In those days, as in these days, there's, many people in the US, especially, and also in Europe, think that the US and Europe are the only two places where you can do world-class science. And I think G N Ramachandran proved them wrong. And he acted, I think, I wouldn't say inspiration, but as an example to people like me who had spent 8 years in the US as a PhD student and postdoc, that it's worth coming back to India and doing, trying to do as well as your peers elsewhere in the world. So, I mean, obviously, the molecular biophysics unit has had a large impact on science in India, especially in the field of structural biology. I should just, I recall a amusing, well, not an incident, but many such incidents. So, for 5 years or so, the NCBS of which I was a member was located on the IISc campus, and every day, or perhaps every other day, I would go with my colleague, Dr. Panikar, on his motorcycle to the coffee boat to drink coffee. And invariably, we would pass the molecular biophysics unit, and I would every time point the building to Panikar and say, that's the citadel of Indian science. And I think it certainly was for some time. I hope it will continue to be. But it, I think, spawned a great deal of exemplary work in the institute, and as the students and perhaps faculty members also went elsewhere in the country, spawned great work elsewhere in the country. So I think of all these scientists in India working in post-independent India who have had the largest impact, I would place GNR right at the top. So the work, of course, is absolutely fundamental in nature, and I work in the field of protein folding, which is part of the general area of protein chemistry. And if I look at the developments in the field of protein folding, computational protein chemistry, over the past 50 years or 60 years now since the Ramachandran plot, I don't think there's been anything of such significant value which have been done, even with the fastest computers which have now working on protein folding problems. So I think it's a great tribute to his, perseverance and persistence, and perhaps I've heard from people that he had a terrible temper, and perhaps due to his temper, that he got his colleagues and his students to do as well as they could. I think that's all I have to say.
That's a good point for me to get to the next discussion point. And I would like to ask Professor Manju Bansal, Professor Vasanta Patabi, Professor Balram, and Professor Yatindra, in that order, if they can share something about what they have inculcated from GNR's, just being around GNR, looking at his style of functioning, or even share an anecdote that will illustrate this point. So, Professor Manju Bansal, to you first, and then Professor Vasanta Patabi, Professor Balram, and finally Professor Yatindra.
Okay. This is a tough one. But the thing is, as I said, I was probably among the various people, the only his direct student who's still alive and working, I guess. So his temper was legendary. There's no doubt about it. And the thing is, at the time when I was his student, we were located in the lecture hall complex in IISc, which meant that when he let go of his temper, it wasn't just the MBU unit people who heard him shout, but all the neighboring classroom students would hear him. And when we walked into the C mess for lunch, invariably somebody would walk up and say, "So who got it this time?" Which was, it wasn't a nice feeling or a very comfortable feeling. But I think we learned to cope with it. But one thing is that I think that was something which, in a way, we learned, I think, to avoid, because while GNR being GNR could, I think, do what he did, I don't think any of us in today's day and age could be, shout at a student or. I mean, he was also notorious for actually, if you wrote something and gave it to him and he didn't like it, he would just throw it back at you. And I don't, as I said, I don't think today that would be acceptable behavior by, I think, most scientists. So I think from my personal point of view, I think in some ways I learned what to avoid rather than, mimic him or follow his lead in that respect. But as I already said in the earlier little module, what I did learn from him, as I said, was trying to do science which was challenging and new, and the other was to take up challenge the other way. And as was pointed out, I mean, GNR took up. He became chairman of this new unit in Madras and went off from IISc to set it up at a very young age. So that just reminded me that when in 2001, when Professor Sharat Chandra and Professor Vijayan asked me if I would be willing to go and start this Institute of Bioinformatics and Applied Biotechnology, I was actually very, very hesitant because I had, again, zero experience, administrative experience, and I really was more interested in my research than in setting up an institute. But I think it was Professor Vijayan who said, "You are a GNR student. You can do it. You go and try it at least." So I think that gave me, and I actually did give it some thought and decided that, okay, yeah, I mean, if GNR could do it at 30, or I was already 50 at that time, I can also give it a try. And of course, I feel very happy, of course, Professor Yatindra, when after, in a way, like GNR, I came back to Institute within 3 years because I was missing the research component in IBAB. So, but I think, as I said, it was challenges at every respect. And in the beginning, we couldn't understand sometimes GNR's behavior, but I think after some time, as his son Hari pointed out, I think we realized that he wasn't quite in, control in some sense. So he had some health issues. But I think my, one of my happiest moments with him, working with him, was when after I submitted my thesis, Mrs. Ramachandran rang me up and congratulated me because it so happened that I was the only woman scientist who had completed a PhD with Professor Ramachandran. So there were all these little incidents, which made up for the problems and which one did face with him. It wasn't smooth sailing. It was a roller coaster ride quite a bit of the time. And because he would praise you, he appreciated when you did anything and the results were to his liking. But at the same time, as I said, if something didn't quite match with his expectations, he could be quite difficult. So as I said, I think one thing it made us realize is that if one could work with him, one could cope with a lot of things in life, even not just in the one scientific career. And also something like his not getting the Nobel Prize, I think it made one realize that it didn't stop him from doing science. So I think it made us realize that you should just, if you just like doing your science, you can just keep doing it and not worry about whether you get some awards or recognition or not. So I think that is what I would like to just conclude.
Professor Vasanta Pattabhi, you need to unmute yourself.
As Manju described, it was a daily happening, He would be angry at times, he would be shouting. Ours is much smaller department, but all of us knew that he had some health issues, so we never took it to our heart because, as she said, I wasn't his direct student. That was another factor. And I was the student of Professor Venkatesan, who was a very calm person. So the impact was not too much on us, excepting that he was a caretaker. Professor Ramachandran was a caretaker. Will take care of all our fellowships. Not a student went without a fellowship. All that he took care of, project, funding, getting the equipments, everything. So I personally, the message I would say I learned from him is focus on science. And once, Professor Kendru visited us and somebody asked him about some equipment. So Kendru said, you don't do science because you have an instrument. You buy an instrument for your research. Similarly, you don't just keep buying things because you need to buy. So we learned to work even without anything. Like after he left, there were shortage of chemicals, there was shortage of funding, lots of problems. But we survived. Professor Srinivasan helped us and we survived. And then I became a faculty. I knew how to do a protein structure without even having 100 test tubes in the department. So basically, it is not just the equipment, but it is just, as she pointed out, that it is the main focus and drive you need, and keep all the students motivated, take them along, give them their credit. This is what I learned from him. Thank you so much.
Professor Balram?
I think there was nothing that you could learn from Ramachandran about management style. You could learn a great deal of science from him. I joined his department when I was a little under 25, and I had a little room just opposite his room. And so for the first several years that I was there, I was witness to some of the most exciting events in MBU's history. And those were good days, but I think the one thing that you could learn from him was, I would really say, his almost single-minded devotion to the research that he was doing. Nothing else really bothered him very much. He was not an administrator of any kind. And I'll tell you just one story about the kind of person he was. Sometime in late 1975, the emergency imposed by Mrs. Gandhi had been in force for about 6 months. And there was no news in the newspapers, so the newspapers would try to get something or the other. And we got a reporter who came, I don't remember now, from the Indian Express or the Times of India, to interview Professor Ramachandran. And at that time, we were trying to get some equipment, some money, nothing was available. And so Ramachandran said exactly what he thought about the government support for science.
The next morning, on the first page of the newspaper, there was headline, "Scientists' Agony, Government's Apathy." And I have never forgotten that headline. This, unfortunately, in those days, Ramachandran was not hauled off to jail for sedition, but it did turn out that he was totally unaware of what was going on and what might be the repercussions of what he said publicly. I think he was a scientist. He was not one from whom you could learn much about the management of his.
Finally, Professor Yatindra.
Okay, I learned from my limited interactions with Professor Ramachandran. I would like to summarize by two phrases. Insist on quality and avoid mediocrity. Achieve the best under all circumstances.
Okay, so with that, I want to invite the youngest panelist, my colleague Gayatri. Gayatri, both you and I are graduates from MBU, and you are also a crystallographer. So how does the message of having been there, I when we were students, it used to resonate in the corridors, about stories of the science and the personality and all that. So how does that reflect on your work today? How does it inspire you, and and others of your batch that you are representing now? Gayatri, you're muted.
So when Rahul first approached me saying that I should be part of this panel where all of you are around and then Madhu is leading the discussion, and he told me that I should be talking about some anecdotes about GNR which is known in MBU. So I said there's no anecdote which I could possibly speak about after all of you and especially Madhu start speaking about anecdotes. So coming to the point of where I'm actually regularly reminded of what GNR has done. So all of you were describing him as a tough taskmaster. I think the point at which we are, as a crystallographer who still builds structures, the point at which Ramachandran always reminds us to be correct is at the last stages of model building while building a structure. So before we submit or deposit the coordinates to the PDB, it's important that there are no residues lying in the disallowed region. Irrespective of how good your resolution is or how well all the automated model building softwares have done their job, there will be one or two residues which lie at the boundary at the allowed region each time in you refine. So our task is to somehow put it inside. And invariably you realize that there is a mistake there. Why it's in the disallowed region is because the adjacent residue, the peptide bond, might be in the wrong direction. So that way, Ramachandran still talks to all of us and corrects our mistakes as we build the structures. So that's a point where every time we are reminded of it, and even now the softwares also call it as like Dynarama. So that's the name of the plot in Coot, the model building software. So it's the dynamic Ramachandran map. As you keep building, the phi-psi values of each residue will keep moving, and the point which we are waiting for is a green signal from the Ramachandran map to proceed with the structure. So that way, a wrong interpretation of the map is always pointed out by Ramachandran still as each of us build a structure. In addition to this, one of the valuable trainings which we have received from MBU, I think, is the rigor with which we look at protein structures and the time we spend with the structure after we build. That has always led to getting new insights from the structures and has led to turning points of my research from PhD, postdoc, and even current day research. I think that's how I would think that both Ramachandran plot and the training in structural analysis, which I have received from MBU, has helped me in my science.
Okay.
And hopefully we'll pass it on to the next generation too.
Thank you, Gayatri. So before we've sort of we've rapidly run out of time. So I'm afraid the audience questions would have to be kept for some time later. But before I can conclude, I want to call upon Mr. Jairam Ramesh to say something about what he knows about the GNR centenary and things that he wants to express. So over to you. Okay,
Sorry, I didn't expect to speak. The last 90 minutes has been in education, and once in a while, people in public life should shut up and listen to others. And I think that's what the last hour and a half has been. I've long been fascinated by GNR, and I feel that he is the one great scientist whom the country has not recognized. He was recognized only in 1977 as an FRS, to give one example. And he got no Padma Awards. He was like many other scientific personalities. I think GNR, whom Professor Udgamkar rated at the top of the post 1947 generation of scientists who worked in India, never got the recognition he deserved. And I have been telling Professor Vijayaraghavan that in a small way we should rectify this and celebrate his centenary appropriately next year. 2022 happens to be the centenary of both Hargobind Khorana and G. Ramachandran. And one epitomized an Indian who excelled in the United States, and one epitomized an Indian who excelled in India. And I think it would be appropriate for us, to celebrate this, build up an archive of GNR, make the new generation of scientists not in the fields of biology and chemistry aware of GNR, and as Professor Udgamkar said, what it takes to do good science, world-class science in India. I think that's the great takeaway lesson that one derives from GNR's life. And I'm so glad that you gave me this opportunity. And I do hope that in 2022, particularly, we will focus on this aspect of GNR's life. How to be in India, build science, as Professor Balram said, a very important distinction he made between building science and building institutions. How do you build science and how do you build institutions? I think these are very important questions that we need to keep in our minds. And I hope the GNR centenary would give us an occasion of addressing these questions. I happen to be the chairman of Parliament's Committee on Science and Technology, Environment, Forests and Climate Change. And one of the things that we're looking at now is how do we renew all these great institutions that were created, in the 50s and the 60s and in the 70s, because institutional revival is absolutely essential. And you revive institutions by renewing people. You have to get younger and younger people through the system. And this is one of the issues that, I'm trying to grapple with in my committee. And I look forward to continuing my association with you. So thank you once again.
Madhu, you're muted.
Yeah, I had to mute myself after telling everybody this. Anyway, so thank you very much for that. And I'm afraid that we'll have to conclude the discussion now on G N Ramachandran's life and works. And you can clearly see that we could have gone on for many hours on this. I want to make this observation in closing, and this is something that is a theme that came up with others too. GNR is perhaps the least well known of the major scientists in India. Professor Vijayan, in his autobiography, mentions that when he gave these popular talks on science, he would often ask his audience, school and college students mostly, to name famous Indian scientists. The answers were invariably, Raman and the Boses and so on. Very seldom, if at all, GNR ever got mentioned. And here we have someone who has contributed so profoundly, influenced structural biology, biophysics, so much so that his work is textbook material. And I'm hoping that this film in some way gives some fillip to having GNR in the national conscience. And so such a colossus, I think, deserves to be remembered and will continue to inspire generations to come. I hope this is what is the outcome of this. So thank you all very much for participating in this. Thank you all very much for tuning in on YouTube and listening to this. And please do send in your comments. Thank you.